All right, welcome everyone. Thanks for those introductions. And as Yasi said, feel free to interrupt with questions. I'm Kevin. I'll be covering, Brian and I are going to split the presentation. So I'm going to begin with a focus on the hardware, and then Brian will give you some information about the software. So the purpose of this webinar is to just give an introduction to Polaris. It's still in the bring up stages. And so this is our newest computational resource, and we're still getting it ready to be stood up. And so right now it's for only internal access, but we're hoping to get wider access on in the second half of this year. And you can see I put a little clip of the latest top 500 list up here that Polaris was number 12. So it's a pretty solid machine. And you can find more information about it on our website as well. So like I said, I'm going to dive into the hardware, and then I'll hand it over to Brian to take on the software. So first, I'm going to walk through basically some of the components that are on a node, and then we'll look at the overall node architecture. So Polaris will be using a single AMD Milan series CPU. So you can see that it's a Zen 3 architecture. We've got 32 cores per CPU. It's got a relatively high amount of DDR memory with 512 gigabytes. The Milan series has 8 memory channels, so that's how you get your relatively high 200 gigabytes a second of memory bandwidth. And it also uses PCI Gen 4, so that's how we will be connecting to the NVIDIA GPUs. So next, to look at the NVIDIA GPU. So if you see on the lower right there, there's a picture of this. HGX is the idea of having multiple GPUs on the single board that you put into a system. So it also goes by the codename Redstone. So in this architecture, each node has 4 GPUs. They're all the A100 factor, A100. You can see these units have FP64 tensor core, so you can get 19 teraflops if you're able to use exploit the tensor cores. There's well as hardware support for various smaller sizes, types for machine learning primarily. And you can see that these GPUs will be connected to the CPU with the Gen 4 at 64 gigabytes a second. But within the 4 GPUs, you can use the NVLink and add a much higher bandwidth to share memory between the GPUs on the node. So now we'll look at the overall node configuration. So if you look at the image on the right, so we see we have the 4 GPUs and the green links representing the NVLink with the high bandwidth between each of the GPUs. And then the red lines, so we have a dedicated PCIe connection to each GPU from the CPU. So you can directly talk to each GPU directly. And then you can see at the top, right now we have these blue boxes. These represent the NICs. And this is an area where I'll go into this more later, but Polaris is still in flux. So currently we're running these Mellanox CX5 NICs, but in the future we'll be running HPE's Slingshot NICs, which is what I have listed in the table on the left. So you can see in aggregate, we have 1.6 terabytes a second for the memory on the GPU, so quite high bandwidth. Also, you can see that we have some local SSDs, and I'll talk about those more later. And so eventually, when the system is running Slingshot 11, I'll talk about this more. You see that we've got 2 NICs each at 25 gigabytes a second. So we've got a relatively good. So now I'll go over the interconnect, and this is a part, as you see, that's still in flux for Polaris. But currently, the system is in what HPE calls Slingshot 10. So that is using the above Rosetta switch. That's a block diagram on the right for it. It has its has similar features if you're familiar with the XE series for their Aries networking. So it has adaptive routing, it has congestion control. And one of the features that Rosetta and HPE has been working on much is to reduce the tail latency. And so that's one of the major improvements for Slingshot. As you see, it also says we have multiple quality of service levels. That feature can, although it's present on the switch, can only be exploited by Slingshot 11. So I'll talk a bit more about that in a second. But some of these features, although the switch enables them, will only be available once we have Slingshot 11. Slingshot 10 means that we're running this switch with a Mellanox NIC in straight Ethernet mode. And so this is what we have currently on Polaris. When users get on, we may still be running this mode. This is why I'm presenting it. But we do plan on this year upgrading to Slingshot 11. And that means replacing the Mellanox NICs with HPE Slingshot NICs. And these have some additional HPC focused features, such as this hardware tag matching. It has its own progress engine. It has dedicated support for some collectives that can be handled on the NIC and the switch, and then special support for one-sided operations. And Slingshot 11 NICs will go from the current 100 gigabits to 200 gigabit performance. So in the upper right, in this area here with Slingshot 11, you'll see we have about 28 terabytes of injection with a bisection of 24 terabytes, and that's what we hope to achieve today. However, currently, if you get early access to the system, you'll have a lower injection and will be limited by this performance for the overall injection for the short term.
Kevin, we have a quick question. Kyle
Yes.
is asking why the nodes are in dual socket for the CPUs. Is there a reason for that? And he's wondering if it's related to the number of GPUs per node.
Yes, we wanted to keep a ratio that was a bit higher. So if we had 2 CPUs and 4 GPUs, that 1 to 2 ratio would not be a good sort of on-ramp to the future exascale systems that have higher, ratios of GPUs to CPUs. So we wanted to keep at least get something similar to that and have a 1 to 4 ratio.
Thank you.
Okay, next, the network itself is what's called a Dragonfly topology. Again, this is similar to Cray's previous Aries network. And so it's a 1D Dragonfly. We have a total of 11 groups, but the compute is split into 10 groups. So if we look at this diagram, each group has 8 switches, and those switches are then connected to each other group. And so within the group, there's a higher total bandwidth between all of the NICs. Then the global bandwidth is a bit lower, so there's some tapering, but you can connect to each group at these given total links. So so you have 9 times 2 links to other groups, other compute groups. So one of the relevance of this is understanding when your job is running on the system. If your job is placed in a single group, let's say you only need, let's say 25 nodes, that's probably the best configuration you can get because you'll have the highest bandwidth and lowest latency when you're all placed in one group. If your job, let's say, needs 200 nodes, if those are placed, or let's give an example of 100 nodes, you could be placed in 2 groups. That will severely limit kind of if you have a lot of communication that's like all to all, because you'll be limited to just 2 links in the global, where you prefer your job to be placed across all 10 compute groups in that case, because you'd have significantly more global bandwidth. And so this is one of the key things that you want to understand if you have, if your job has significant dependency on communication. And so we're of course still tuning our scheduler to get the good heuristic for placing jobs. All right, and so kind of to now round out the overall system. So we have a total of 560 nodes. We haven't decided how those nodes will be split up. Like there may be a debug queue. So some of the, like the largest total size of a job you'll be able to run. I'm not sure yet, but we do have 560 nodes. We can see that gives a total of 2,000 GPUs, which is a fairly good on-ramp again to these future exascale systems if you can run on all 2,000 GPUs. And finally, at the bottom there, you can see as far like our peak for HPL, we can get 44 petaflops from the system if you can utilize the tensor cores. All right, and now moving on to some of the storage. So as I said before, each node has 2 SSDs for local storage. The total capacity is enough to sync all of the memory that's on the node. So if you want to do some kind of local checkpoint, you can do so. This is also similar to Theta, where we also support local storage for users. Similar to Theta, we don't have a dedicated software for using it. The volumes are just provided as ext4 or XFS volumes. And so it's the user's choice of how you would like to use this. Like, so if you write data there, if you want it to be accessible to some other node, you'll have to provide a mechanism for that. As well as the fact if you want that data to survive your job, you'll need to manually copy that from the local storage to one of our main file systems. But again, it's an option there that users can take advantage of. And finally, Polaris doesn't have a dedicated storage system. It'll be using our existing storage systems. And so depending on how well you're keeping up to date, ALCF has recently, somewhat recently deployed 2 new file systems. They're called Grand and Equal. They're both identical in hardware, so they're each 100 petabytes and have the same general throughput of 650 gigabytes a second. Grand's more the general project file system, whereas Eagle has some additional support in Globus for Globus sharing. On Polaris, we will connect to these through LNet nodes, which are gateways. And so these gateway nodes could, they're all fully provisioned, could provide up to 1 terabytes a second. That'll be a little bit depending on how as well as the network architecture can support that from end to end. But that means you can probably saturate one of these file systems, but certainly not both at the same time. But we should be able to fully utilize one of these cluster volumes. And we will also have our home, which is shared with our other existing systems. So if you have a current account and the home file, your home file system will be the same eventually when you get on. Currently, we use a different one. So if for some reason you have early access to Polaris, you would be using a different home than you would have on other systems, but eventually they'll be merged into a single shared home. That kind of concludes the hardware section. Is there any, I see there's some comments in the chat. Is there any other questions?
Yeah, I think there are a couple. So Alfred is asking about the number of compute nodes, 8 by 10. I'm not sure. So 10 groups, each group has 8 nodes. That's what he's asking.
No, we have 10 compute groups and Dragonfly, and each of those has 56 compute nodes in it. I can go back to that chart if that was a question here. Sorry, here. So you can see each group is composed of 56 nodes.
Yeah, okay. So the other question is, does it support NVIDIA GPU direct storage?
There's no technical reason why it cannot. We haven't configured that or tested it yet, but yes, that should be possible.
Thank you, Kevin. So before we move on to the next session, which is on the software side, do you guys have any other questions related to the hardware? And yes, the slides and the recordings will become available. I don't see any questions. Okay. Thank you, Kevin. And right. You're going to be on the chat, I believe. Yes. So if you guys have more questions, you can ask there. And Brian, please.
I'll stop sharing so Brian can share. Yep. And while Brian's bringing up his slides, I will just offer this one remark that the storage is relatively, or I'm sorry, the overall hardware is relatively set in stone. whereas software is far more malleable. And so what's being presented here is kind of the current status. That doesn't mean things won't be changed and won't be different when users finally are able to get on.
Yeah, that's a very good point.
Okay. Hello, everyone. So I'm Brian Homerding, and I'm going to provide an overview of the software side of Polaris. As Kevin has mentioned, the system is in flux, but this is going to provide a high-level overview of what's kind of available or can be used on the system. So from a high level, Polaris is going to provide an excellent platform for preparing your application codes for Aurora and the other exascale system. All of the programming models which are available on Aurora can be tested on Polaris. And the main programming environment is provided by HPE, the HPE Cray programming environment. Polaris will provides excellent capabilities in simulation, data, and learning, all through the NVIDIA's existing HPC SDK, which is available. And there's support for HPE's Cray MPI and MPICH via libfabric using a Slingshot provider. So as Kevin mentioned, the file systems on Polaris, there's a shared file. There will be a shared home file system. Right now it's a dedicated one, but when you get on, it'll be shared with their other homes. You all also have access to the Grand and Eagle file systems, which are mounted under Lust. You can access under Lust Eagle, Lust Grand. So overall, this gives you access to your main project storage through Lust Grand projects and your community project storage through Lust Eagle projects. So when you get on the system and you actually want to start accessing things. So for requesting resources and submitting your jobs on Polaris, we're going to be using the PBS Professional scheduler. This will be changed from the Cobalt scheduler, which is used on Theta and Cooley. Many of the primary commands are similar, however, the options are different. So some of the main commands that you're going to want to be using, you'll likely use for most of your jobs, either qsub, which allows you to request your resources and you'll start your script on the head node. This being another change is that the script will run directly on a compute node, with the head node being the main compute node which the script runs on. You'll have similar options like -A for your allocation that you're going to be using. And then you'll specify a lot of your selection and requirements for your job through the -L, which provides the various options. And I'll go through a few of those examples on a later slide. Another important command is the qstat. This allows you to check on the status of your requests or on the queues in the system. So important one being qstat -Q. This will give you a list of the queues that are available to submit to. Additionally, you can get kind of more verbose and complete information about your job with the -F parameter by passing it your job ID with -F flag. And one of the features available with PBS Professional is access to historical data or completed jobs. So if you use the -S flag, X flag, with your job ID, you can get that information about a completed job and even the full information about the completed job with the previous flag. Two other important commands to be aware of are the QAlter and QDelete commands. QAlter allows you to update your requests. This could be something like wanting to change the wall time if you had a typo in your submission script. So you'd be able to change the wall time for a job that has not started running yet, or QDelete if it turns out you want to cancel that request. So there's a few other useful commands that we've run across. One of those is qsub to PBS. Now this is available on Theta and Cooley right now. And this is going to help you to basically migrate your workflow over to Polaris. So what this is going to do is translate your Cobalt qsub command into a PBS qsub command. Put it simply, you'll pass it your Cobalt command line and it'll give you the PBS one that you can use on Polaris. That being said, it's a general tool, so it's not going to be specifically targeting Polaris. So you will have to make a few changes to specify that you're targeting the system Polaris. There's also the PBS nodes command, which can provide you some information about the current state of nodes on the system. So for running your MPI applications, as I mentioned earlier, the jobs will run directly on the compute node. So now instead of using the AP run, you'll be using MPI exec. So this command will run your applications using the parallel application launch service PALS. So basically you're going to use MPI exec to execute your MPI applications directly on the compute nodes. So there's a lot of different options for controlling your launch, but some of the main ones that we see regularly used include -n for the total number of MPI ranks you're going to be running, -ppn for the total number of MPI ranks per node, CPU bind in case you want to specify the CPU binding for the application, the depth, which can allow you to specify the number of CPUs per rank, env, which allows you to set environment variables, one of the important ones being OpenMP num threads, so you can pass that through the env option, and host file, which will indicate which file contains the host names, and this should be set by default for a kind of normal usage. As always, you can get the full list of options which are available and additional information from the man pages when you get on the system. Well, there's many different ways to control your MPI execution. A few of the kind of environment variables that we've come across that are very useful in the system include the MPIC GPU support enabled. So this essentially allows MPI operations to use communication buffers, which are on GPU attached memory regions. This should be enabled by default, but it's something to be aware of. And then a few other options for kind of understanding how you're mapping to the NICs and using them. So if you want to get kind of verbose information about the NIC selection for your application, you can use the MPIC OFI NICs verbose environment variable by setting it. And then if you want to control this mapping, there's a couple of different ways. So the MPIC OFI NIC policy, this allows you to give it a different assignment policy, the options being block, round robin, NUMA, GPU, and user. Or you can use the MPIC OFI NIC mapping to specify a specific rank to NIC mapping for each node. So as I mentioned earlier, the main programming environment is the HPE Cray programming environment available on Polaris. It provides the HPE Cray MPI support, which allows for PGI offload to the A100s for multi-NIC and multi-GPU support. This has full support for the Rome and, more importantly, the Milans. There's also the NVIDIA HPC SDK, which can give you a use case for programming on the A100s, along with the other programming models available. And then there can be support for the SYCL and data parallel C++ for running on these nodes, either through the CodePlay Compute CPP compiler with NVIDIA support, or the LLVM through LLVM with the Intel DPC++ branch, which offers support for offloading simple code to NVIDIA GPUs as well as the Intel GPUs. So to give you a kind of high-level view of the programming models and kind of how they're going to relate to the exascale systems. So on Polaris, you'll be able to run MPI plus variety for launching off to the GPU. So this includes OpenMP, OpenACC, CUDA, DPC++, SYCL, and HIP. Those are being the vendor-supported programming models, but also the ECP-provided programming models, Cocos and Raja. Now, there's several compilers that can be available for these different systems. For OpenMP, you have access to either the NVIDIA compilers through the HPC SDK, or the Cray compilers, or LLVM itself, the upstream version. Then NVIDIA provides support for OpenACC and CUDA. And as I mentioned earlier, LLVM and SYCL both have a support for DPC, or CodePlay have support for SYCL and DPC++. And you can use AMD's HIP to run on the system as well. And then for Cocos and Raja, you are able to basically run those with a variety of backends, including the CUDA backend, which is more targeted for the A100s, but also any of the other backends which work, such as the OpenMP target, or even SYCL and HIP if they're portable to the hardware. So HPE, the default Cray programming environment, provides Python with several built-in modules, which are very useful just in there by default. Things you're going to want like NumPy and SciPy and Pandas. and then the very important MPI for Pi, which is very important for running on a system to scale. Additionally, there's many optimized data learning and analytic frameworks that are available for the NVIDIA libraries. So these include, for data learning, you can have TensorFlow and PyTorch, which are optimized to use cuDNN. And for distributed data parallel deep learning, libraries like Horvath are optimized to leverage NCCL communication, the library from NVIDIA. For data analytics, you can make use of the NVIDIA Rapids library and also make use of their Python environment, which includes a Numba for GPU that uses the CUDA backends. The Cray HPE provides an AI stack, which includes the hyperparameter optimization library, along with support for running and operating your Jupyter notebooks, and the Smart Sim library, which can be used for in situ coupling of simulations with analytics and learning. You can also make use of the Spark Big Data Stack, which has modules optimized for GPUs. And you can kind of wrap all this up and use a container environment, which is based on Singularity. Singularity is currently available on the system, though it's still being tested and worked on. So there's several debuggers and profilers which are available on the system even today. So the stack for debuggers, you have access to the stack trace analysis tool stat, which allows you to do stack tracing at a scale. You have GDB for HPC, which is a parallelized GDB that's specialized for HPC, and CUDA GDB, which is useful for debugging your CUDA code. For the profilers, you have access to the performance analysis tool PAT, which gives you whole program performance analysis, and also the NVIDIA Insight suite, which provides system-wide performance analysis and can be very useful for understanding your performance on the A100 GPUs. So as always, if you're looking for any additional information or help, one of the first places to look is the Support Center on the ALCF website. This includes all the documentation for the ALCF resources, and will soon include the Polaris documentation as well. You can see the additional information about Polaris on its main page, the Polaris page on the ALCF website. And as always, if you're needing any help, you can get help for your ALCF resource usage through support@alcf.anl.gov.